Inelastic mechanical properties govern the behaviors of a wide range of everyday objects. Simulating them attracts a lot of interest in computer graphics. We propose ECI, Energetically Consistent Inelasticity, enabling robust, accurate, and efficient simulations with large time step sizes. Our contributions include an implicit internal force formulation for fully implicit finite strength elastoplasticity, a strain energy augmentation method that uses analytically integrable elastoplastic forces and symmetric force derivatives for form versus straight-to plasticity. An extension of our model to support strain hardening, pressure-dependent soil plasticity, and rate-dependent viscoelasticity. Algorithms for incorporating our model in optimization-based time integrators with the material point method and finite element method. Now we introduce our ECI, Energetically Consistent Inelasticity model. Under the finite strength framework, the deformation gradient is decomposed into a plastic and an elastic part. The plastic deformation changes the rest shape, and the elastic deformation produces elastic forces. When a stress is outside the pure elastic region, the stress is pulled back onto the yield surface by the return mapping applied on the strain. Our formulation of internal force with implicit plasticity is as follows. Replacing the undetermined future states by the previous time step, we get the explicit force under plasticity, which was used in Clark et al. 2016. However, their implicit formulation extended from the explicit force is not equivalent to the force with our fully implicit plasticity. The force on the semi-implicit formulation is not equivalent to the fully implicit force either, where the elasticity and the plasticity are completely decoupled. Our variational model stems from a close investigation of a one-dimensional elastoplastic spring. We discover a variational form for the force of spring with constant yield stress. The augmented part is proportional to the deviation of the trial strain away from the yield strain. Under this model, the results from our implicit time integration with a large time step size matches the reference generated by the explicit time integration with a small time step size. Without hardening, the form misses plasticity or J2 plasticity is associated with a constant yield stress. It has a variational form similar to the spring. For other plasticity models such as Drucker-Prager, we extrapolate the yield surface in the principal strain space to achieve volume-preserving projection for the definition of the augmented part of our elastoplastic energy, and use iterative yield stresses for the integrability of forces. The force equilibrium and yield stresses are solved alternatively. At each iteration, each particle experiences a locally constant yield stress. We simulate a column of sand collapsing on the ground with the Drucker-Prager plasticity model to compare our model to existing ones. The time step size of the explicit method in Clark et al. 2016 needs fine-tuning to avoid explosion. For their implicit method, the time step size requires fine-tuning as well to ensure convergence and maintain stability. The semi-implicit method results in severe artifacts even with a small time step size, and the results are not consistent when using different time step sizes. Instead, our method produces consistent high-quality results for both small and large time step sizes. Snow can be modeled using Drucker-Prager plasticity with cohesion. We simulate a snow castle hit by a high-speed elastic fish. Using our method, the castle is smashed into intricate pieces as expected. However, with the semi-implicit method, the castle behaves more like an overly cohesive elastic body, which is unrealistic. Next, using the same model, we simulate a snowball hitting a dragon on the ground. The trunkiness of the snow can be conveniently controlled by using different cohesion strengths in our model. Leveraging NPM's automatic handling of topology changes, we simulate a Play-Doh modeled by the form misses plasticity pressed through a cylindrical noodle mold. Our variational plasticity model is independent of spatial discretization. The following examples are simulated with the finite element method with the incremental potential content model. The hardening effect is widely observed in metals. Here we simulate hydraulic tests on soda cans with different hardening coefficients and compare them to the one on the right without hardening. A larger hardening coefficient causes more restoration towards the original rest shape. With the hardening mechanism, we can successfully capture the well-known snap-through instability. The deformation patterns on the blue can simulated by our method matches that from a real experiment. Next, we conduct a hydraulic test on a long cylinder pipe, where the crushing pattern also matches a real experiment shown on the right. So does the square pipe. Now we simulate a high-speed racing car crashing into another parked car, creating a significant crease dent on the side. We also simulate a plastic armadillo rolling through a crusher. The shape of the gear teeth is printed on the armadillo permanently. Our variational inelasticity framework also supports viscoelasticity. Here we simulate a hand pressing down on a memory foam pillow for a while to leave a handprint on it, and then moving away suddenly. The handprint slowly disappears as the deformed memory foam gradually restores its initial rest shape. For more technical details, please refer to our paper. Thanks for watching.